In this video I am going to discuss about capacitor in parallel combination. A capacitor is a two-terminal electrical component. Along with resistors and inductors, they are one of the most fundamental passive components we use. I already discussed about capacitor in my previous video. You can find the link in description. So here we can see the circuit. One capacitor is connected together with a DC power supply. I am going to add two more capacitors are connected to each terminal of another capacitor. So we can say that three capacitors are in parallel combination. The voltage V connected across all the capacitors that are connected in parallel is the same. Then, capacitors in parallel have a common voltage supply across them, giving Vc1 equals Vc2 equals Vc3 equals V. In the following circuit, the capacitors C1, C2 and C3 are all connected together in a parallel branch between positive and negative terminal of power supply V, as shown. When capacitors are connected together in parallel, the total or equivalent capacitance CT in the circuit is equal to the sum of all the individual capacitors added together. This is because the top plate of capacitor C1 is connected to the top plate of C2, which is connected to the top plate of C3, and so on. The same is also true of the capacitor's bottom plates. Then it is the same as if the three sets of plates were touching each other and equal to one large single plate, thereby increasing the effective plate area in meter square. Since capacitance C is related to plate area, the capacitance value of the combination will also increase. Then the total capacitance value of the capacitors connected together in parallel is actually calculated by adding the plate area together. In other words, the total capacitance is equal to the sum of all the individual capacitances in parallel. Also, we can find total capacitance of parallel capacitors is found in the same way as the total resistance of series resistors. Here you can see the current is splitting in each capacitor as I1, I2, and I3. So the total current it is equal to I1 plus I2 plus I3. We can write I1 is equal to C1 dV by dt, I2 is equal to C2 dV by dt, and I3 is equal to C3 dV by dt. Then we can define the total or equivalent circuit capacitance CT as being the sum of all the individual capacitances added together. We can also define the total capacitance of the parallel circuit from the total stored Coulomb charge using the Q equals CV equation for charge on a capacitor's plates. The total charge Qt stored on all the plates equals the sum of the individual stored charges on each capacitor. Therefore, as the voltage V is common for parallel connected capacitors, we can divide both sides of the above equation through by the voltage, leaving just the capacitance, and by simply adding together the value of the individual capacitances gives the total capacitance CT. Also, this equation is not dependent upon the number of capacitors in parallel in the branch, and can therefore be generalized for any number of n parallel capacitors connected together. I hope you understood parallel combination of capacitor. If you like the video, please hit the like button and subscribe for more such videos.